Hello. All right, maybe it's time to start. Seems like none of you have any question from yesterday's lecture. So one of the thing we discussed yesterday uh, is the idea of a norm on CD, and to define the norm, we use another structure. This is the inner product, right? So maybe I put a dot to emphasize here. So although we have an abstract definition of norm, but in this context, we get it using inner product. Now, again, the same question. If we just have a vector space, then do we have the structure of an inner product? And the answer is no, because if you look at these axioms of vector space, then this doesn't include anywhere, or none of these axioms imply this must exist or should exist. Yeah. So, like yesterday, we introduced norm uh, as a generalization of this. Now we are going to introduce inner product space as a generalization of the inner product in CD. So let us start. Inner product space. All right. So as we talked yesterday, although some of the notion can be defined for more general field, but we are concerned only on either complex or real. So as before, we will consider a vector space. So V is a vector space over K, and by an inner product on V, uh, an inner product on V is a map. There are several notations. Let me use this one, so which is a map from V to V, V cross V to K, which satisfy some properties. And these properties are strongly motivated from the property we have seen in RD or CD. So, what are the properties such that? So, if you have some number, so C, and you have U plus V. So UV is an element. Okay, maybe I should first write this more rotationally. So UV maps to UV. Yeah. Okay, now what are the properties we need to satisfy? The first property is that we have some number C, and then you have C U. So this is a scalar multiplication plus V, and then we need something in the second slot. So we put in W. This equals to C bar. By C bar, I mean complex conjugation. U W plus V W. And next, so by an inner product, we mean actually an Hermitian inner product. Sometimes people write Hermitian product also. So Hermitian property, which means that U V, this is it can be complex or real. So say this is a complex for the time being. Then what if we change the order? So VU, then we do complex conjugation. Of course, if it is real, then this condition, the conjugation is void, right? And the last one is V equals to, sorry, it's positive for all x. So this is the positivity requirement. And in particular, if we have the equality, that means V equals to 0, that means that V itself is 0. And a vector space. So the field is now, since fixed K, we are not changing. So let me not write this notationally. And endowed with an inner product is called an inner product or inner product vector space. So is this, sorry, there is a question I haven't seen. Approximately when the recording will be uploaded? Um, okay. I need to talk with other organizers, like how they wanted to do. I do not know exactly what we do, but roughly speaking, I expect that maybe after every week's lecture. So this week there is 3 lectures, but usually other weeks there will be 2 lectures, sometimes one. So my intuitive plan is to do after 1 week's lecture. So is that okay, or you want to upload it immediately after every lecture?
Immediately after might be better.
Okay, then I shall talk with other organizers and we try to accommodate your wish. All right. So, are there any questions regarding this definition?
Sir, will the inner product always be positive or it depends on the K?
Well, so inner product is always positive. Yes, you can define even inner product more general field. Then positivity is tricky. But the setting we are working only in R or C, and then is positive. But uh, there is a further generalization of inner product, which is called a sesquilinear form, and then this is not necessarily positive. And this can be also happen in C or R. So this generalization, if you want to call, that arise naturally, for instance, if you consider spinors. So the natural inner product on the space of Lorentzian spinors is not always positive definite or positive. Yeah, so this cannot be satisfied for this space of Lorentzian spinors. And then you need something called sesquilinear form, which has these two property, but without this one. In fact, if you do quantum field theory in Minkowski space-time, then this also need to be relaxed. So it may happen this is zero, but it does not imply the vector is itself zero. So this is something called semi-inner product. Okay, so this also exists. And of course, if you relax K, then you have even more possibility. But since we will be only interested in K, for us, inner product means a Hermitian inner product, and that's the thing. But again, there is a bit of arbitrariness depending on the author, but it's not something I came up with. Okay. Any further question? Okay, not at the moment. So let us continue. So some of the properties of inner product, I am just writing as properties, but as you know, in mathematics, everything is either a theorem or definition. So these are theorem, proposition, corollary. And for first few lectures, I shall be skipping almost every proof, not because I want to do it or I like to do it, because of time constraint. We will mostly do proofs for operators because that's the primary objective of this course. Of course, everything is important, but you have to make a trade-off. So if you have question, feel free to ask. You will be given some homeworks for your tutorial, so you can get some idea of the proofs if you are not familiar. But yeah, this is something trade-off. Yeah. Okay, so I write as just properties. So perhaps one of the most interesting and useful property is the so-called Cauchy-Schwarz inequality. What does it say? So again, we have this inner product, and we take UV as before. One thing I forgot to mention. So the convention I used, this is anti-linear in the first place or first component, as you can see from here. Some author use anti-linear in the second component. It's just matter of choice. Okay. Okay, so and then you take its absolute value, and these two person prove that this is u, so inner product of this, and you take a square root, and then v inner product, you take this square root. So unless I mentioned what is uv, it has to be understood in the sense of for all uv. Okay. I think you have seen this already, at least in the sense of RD or CN, right? This supposed to be. Okay. Now, some of you wanted to see an example of incomplete normed space and sort of thing, and I told you to postpone until today because I want to introduce a norm which is naturally given by the inner product. And then I want to discuss this, not because it cannot be discussed in general setting, but since our interest is mostly on Hilbert space, so I wanted to come in Hilbert in this structure. So given an inner product as given here, there is a natural norm and we already know what is norm. So norm of V given by, you I think can guess from here, we are now imitating exactly this structure, and that's why we started with this. So that, and that's another motivation, right? We talked about, like, to introduce inner product. So this is norm squared, and you take positive square root. Okay, so this way we see that, okay, once we have inner product, we can get the norm. We can also come the other way around. Okay, and that's how you do it. So say we have norms, form some norm vector space, and then we can define an inner product like this way. So inner product given by 1 by 4, and then you take u plus v norm squared, and the other way around with minus u minus v norm squared. Now, so now I'm writing for complex field. So I times u plus iv norm squared minus I times u minus iv norm squared, right? This. So here we have k equals to c.
Does it also hold where k is not c?
Yes, it holds. So if k equals to, say, r, then you have only these two parts.
But I think that doesn't directly follow from that, right?
No, it
This
follows
is
in the sense
probably
that,
not a general formula for any field k.
oh no no. So because if you go for general field, because you see, I mean, it follows in the sense that you have to use this condition, and this condition for r is just, okay, same thing without the bar. So when you use that, then you go back there. Okay, so these are only a few properties I wanted to show you, and now we come to say main topic, or one of the main topic. So remember, yesterday we talked about complete normed spaces, right? So to talk about completeness, we need some notion of distance, and normed space has naturally distance norm. But now, once we have an inner product, we also have a norm, so we can ask same question about inner products spaces, right? And now we can, so yesterday we have this discussion whether all normed spaces is complete or not, and the answer is no. If it is complete, then it has a specific name, and that's called Banach space. And same vine, if an inner product space is complete, then this is called Hilbert space. So I believe this definition is known who are from math physics background, because that's how you start quantum mechanics, right? So in quantum mechanics, you have the Hilbert space, and that's what's give you the Hilbert space is the complete inner product space. But sometimes in physics books, they don't really discuss what is meant by completeness, and now you know. Okay, so is there any question regarding what is a Hilbert space?
Did we define completeness?
Yes, we did yesterday. So we can go back here. Okay.
Yes.
So complete as a metric space in the sense of Cauchy convergence. So you can also say that Hilbert space is those inner product space, which is a Banach space from the norm induced from the scalar inner product. Yeah, same definition. Any further question? Well, if not, then let me go maybe first some examples that you wanted to know. But before example, I wanted to ask you a question. So whatever we discussed here, so the notion of inner product, so the vector space can have finite dimension or infinite dimension because we haven't mentioned anything about dimension here, right? So say V is a finite dimensional vector space. In that case, is it true that every finite dimensional vector, so in that case we can still have the norm like this and we still have this notion of completeness. Now the question is every finite dimensional vector space complete? So maybe I go for a poll. What do you think? Okay, let me know what you think. Okay, since we are in a saturated situation, around 80% of you have participated. Thanks for all of those who have participated. So I shared the result, and most of you, 62% thinks every finite dimensional vector space is complete, and yeah, around 40% of you thinks this is not true. So now, can anyone who thinks this is true can share us why you think that is true? You can write in chat or just say.
Sir, if the norm is in B, then the Cauchy sequence will also converge in the limit of B at B.
Yeah, that's precisely. So for finite dimension, we have actually all norms are equivalent, and that's why there is no issue. And that's the reason when we talked about linear algebra, or we learned in linear algebra, usually we do not see the notion of completeness because we don't need it. So let me introduce shortly this idea of equivalent norm, and then just give you a bit formal tool. So now we are actually back to a norm space setting, although you can think the norm comes from this way, but it's not necessary. Okay, so maybe it's a recap. So now we are in a norm space setting, and it may, let's assume there are two norms on here. So one norm is this one, another norm, okay, maybe one is not a good notion because we need one letter, another one is tilde. Okay, so these two norms, tilde and without tilde, are called equivalent. So this and this are equivalent if there exists two constants, constant and constant tilde, which are positive, both are positive, such that you take norm with respect to any element, so I don't write anything, and you multiply with this constant. This is bounded by the other norm, tilde, and this is bounded by the other constant, tilde. Okay, so then it's called equivalent. Now we also seen yesterday, once we have a norm, we have a natural notion of a metric space. So let's call dist and distance tilde are the distance induced by these two norms. So when we have a distance, then there's a way we used convergence, right? So we have a notion of topology, we have a notion of convergence, and all the nice thing. So now the upshot is, maybe I write as a theorem because it's fundamental. So we have a norm vector space with two norms, or at least two norms. Okay. And then we have the respective distance. So V distance, maybe this. Okay. Then, oh, sorry. Then this and the tilde are equivalent if and only if dist and dist tilde are equivalent matrices. Okay, so that means once we have a norm, then we can, so basically going from norm to distance or matrices is same in this setting. Okay, now let's back to the question as one of our participants answered already. So to go there, let me first. So we have discussed it, but maybe it's good if we um, recall here. So now we are in the setting of our field, okay, and we have modulus or absolute value, and this is complete from real analysis. We know complete. So, and since this is complete, that means this is a Banach space. All right. Now we generalize this to some finite dimension D, and we want to make this also a normed space, and then we talk about whether they are complete or not. In other words, whether Banach spaces. So to go there, what we need to introduce norms. So some of the norms are like this. So Z, this is the so-called one norm. That's why I don't want to use this notation before. So what you take each element from K, D equals to 1, 2, 3, and I equals to 1 up to D. Okay, this is the one norm. So it's basically sum of individual component at absolute value. But this is not the only norm. You can define another norm. Say this so-called P norm. What does it mean? So instead of taking just absolute value, you say, okay, make life more interesting. I take absolute value to the power P. P is 1 to some integer, but not infinite. Okay, infinite is not any integer. And as before, you sum from 1 to D. And since you have make to the power P, kind of make things system symmetric, you take P to square root. And now you can ask, what about if P goes to, okay, so P 1, 2, ... You can ask, what about P goes to infinity? And we have seen also a prototype of this yesterday, and that is the supremum norm, right? And if you recall, now this is just max of this function and over what? All the indices. 1 ... n. So this is the supremum norm. So now you see that, so it's basic. Sometimes we also include infinity in the P, but then we have to understand the definition of P norm and P infinity, infinite norm are not same, but we just sometimes call, P norm. Okay, so as you see, we can define different sort of norm. And the question I asked is based on the fact that theorem, if the dimension of a vector space is finite, then all norms on V are equivalent. And that's what you told, right? The proof is not that hard, but yeah, you have to work a bit. And now, as a corollary, all finite dimensional vector spaces are complete. Okay. So that's answers. Hopefully that clarifies our answer why in the case, and that's why in linear algebra you probably never encounter the notion of completeness, and that's one of the things that differentiate between finite dimensional and infinite dimensional situation. So sometimes, uh, at least in physics, because I studied physics for a while, and then there is a cultural slogan, let me put this way, is that what you can do in finite dimensional situation, more precisely with matrices, you can also do with operators. And that actually implicitly assume this thing, that whatever is true in finite dimension, more or less is also true in infinite dimension. And that is a horribly wrong statement. And part of this course is to really pinpoint some of the differences in the context of operators, and you have already seen one instance of that. So there is the question, phase space versus Hilbert space. Why do we need Hilbert space? Does it really hamper much of physical understanding? Okay, so let me come. So phase space versus Hilbert space. So I don't understand. What do you mean by phase space versus Hilbert space? You mean that which one is interesting or which one is necessary? Or is this the question, why we need Hilbert space, not the phase space? Is that your question?
In classical mechanics, we already have a phase space. So for quantum mechanics, why we need Hilbert space?
Okay. So one reason is that one of the postulate or main postulate of quantum mechanics is this algebra of canonical commutation relation. And we will actually prove there is no finite dimensional vector space where this can be true. So if you want this relation, quantum mechanics tells us you have to go to infinite dimensional setting. And in fact, historically, so we are in 2026, if you go back 101 years before, and in Germany, so then there was a young postdoc in Göttingen who tried to understand the spectral lines of hydrogen atom, and he came up with some manipulation of array of numbers, and his host realized that what he is doing is actually matrix multiplication. And that postdoc was Werner Heisenberg. And perhaps you understand that's the beginning of matrix formalism of quantum mechanics. So if you want to do matrix formalism in quantum mechanics, there is no finite dimensional situation. Now we can say, okay, there is no finite dimensional situation, but why we need Hilbert space? Why not something else? We will discuss it quite detailed later, but for the time being, one thing is in quantum mechanics, we know probability to conserve. And to conserve probability, we need a special case of Hilbert space, or a specific example of Hilbert space, the so-called L2 space that we are going to discuss today. So part of, say, answer of your question is that if you want to do it, then you need some infinite dimensional. And why this is precisely some Hilbert space, we will see in a mathematical way later. Okay. Regarding classical mechanics, it's true we do not need Hilbert space approach in classical mechanics, but sometimes you can also do, and sometimes you also need infinite dimensional space in classical mechanics. For instance, when you consider solution space of a hyperbolic equation like wave equation, so the solution space of a wave equation is infinite dimensional. So even in classical mechanics, if you want to consider, we have this discussion. So let's go there. Here. So this is the wave equation, right? And this is the solution. And if you ask what is the dimension of the solution space, then you will see it's infinite dimension. In fact, for most of the hyperbolics, this is a very typical of hyperbolic equation. On the other hand, if you take an elliptic equation, like Laplace equation, then the solution space is finite dimensional. So in classical mechanics, infinite dimensionality also arises depending on what you are doing. If you are in a relativistic setting, then naturally infinite dimensional solution space arise. Not take literally, but say loosely speaking. And if we are non-relativistic situation like Laplacian, then usually the solution space is finite dimensional. So this infinite dimensionality arise also say non-quantum setting, yeah, in a way. Another question, does it really hamper much of the physical understanding? It depends on what you mean by physical understanding. So Hilbert space are not something physical, right? In quantum mechanics. So these are like Hilbert space, loosely speaking. If you take pure state, then pure state belongs to some Hilbert space. And these are not any observable. So we cannot really experimentally detect, say this is what is going on. But this is essential for our understanding of quantum mechanical framework that we will also discuss shortly, later part of this lecture. Now, if you really want to understand everything in a proper way, I mean, okay, proper means that you really want to understand what means what. Then you need it, because if you do not know what is the difference between, let's go here. Yeah. So if you do not know what's the difference between these two situations, so this one and the infinite dimensional situation, then even physically, when you try to model something physically, then how can, for instance, you deduce something might not true only in infinite dimension, but true in finite dimension? This can happen. And for instance, in quantum physics, one of the instance happened in the difference between quantum mechanics and quantum field theory. So if you look at one particle state and Fock states, so in quantum field theory, Fock space are infinite dimensional thing. And quantum mechanics, you don't need for, because you don't have particle creation, so you have finite dimensionality. And this has some physical implication, in the sense that if you look at the entanglement structure, then certain thing happens because of finite dimensionality, not for infinite dimensionality. So if you are familiar with this modular localization, then this is what it shows very clearly. So it is not true that these are only some say theoretical understanding. It doesn't have any concrete physical consequence. It has sometimes physical consequences, but not always. Now, coming back to your question, where it doesn't have any physical consequence, then is it interesting or important to understanding? Then it, I would say, depend on your taste. If you are more inclined towards what is called theoretical physics, I don't want to divide in a narrow sense, but loosely speaking, then most of the physicists think this is not important, because they don't want to understand why these spaces differ from that, because end of the day we do some experiment and experimental test, and this experimental result doesn't depend usually on this understanding. So that's why they are not interested. So you look at some standard book in quantum mechanics, then you will hardly find this discussion. On the other hand, if you call what is mathematical physics, again there is a different version what is should be called mathematical physics. I am not going to that debate or discussion, but say those who thinks at least fundamental physics can be formulated in a mathematical setting. It may not be true, but who thinks this is possible, they really care about thing. And part of this is what is part of this mathematical physics, where they think this is important and they want to understand this thing. And as I told, sometimes as a byproduct of this understanding, you can have something which has phenomenological consequence, but not always. So I let it to you whether it will hamper or not. Yeah. And also I told you about this community a bit. So D is dimension. What is meant by multiple norms? So D is the dimension of the space here. So if D equals to 1, then it's just K or C. And multiple norms means you can define several norm in this space. So this is a valid norm. Okay, this is a special case of that. I just wanted to motivate, so I wrote first this. But this is a norm, you can use this. This is another norm. So why not to use this one? Why to use this one? Or how we decide which norm to use? Sometimes there is a choice, sometimes we don't have. So that's why we introduce several norms, and then the result is that, okay, if you're in finite dimension, you may have different norms. If you not, then of course there is no discussion. But if you have, then they will be equivalent as a metric space. So does it answer all of your questions, or you have, feel free. I mean, that's the most, I would say, interesting part that we discuss. All the definition are in book. I'm not writing anything that's not written in the book. All right, since that's not the case, so let me then put forward. But yeah, feel free again to have questions. Now let me introduce some functional spaces. So, okay, let's just put it. So let Kn. So this is the space of all the sequences. Okay, let me denote. Okay, let's keep continuing with Z. Zk, and K is in n set of integers such that Zk belongs to K. Yeah, that's, I think, understandable. Sorry. For all K in n. Okay, I think it's notationally fairly well understandable. Now there is this so-called L, small l. Okay, if you look at LaTeX, it's backslash L infinity spaces. So Z is in this Kn such that all the sequences convergent. Oh, sorry. This is bounded. Convergent is the later one. And next we go for the convergent. So C Kn. This is convergent. Okay. You can define some subspaces of this. One thing is C0. Okay. So yeah, I can also write same way, where the sequences are, or that is, the whole thing is a null sequence. Another one, E, okay, same as before, where all the sequences are finite sequence. Okay, now some more spaces. So this is not strictly speaking, these are usually called sequential spaces or sequence spaces, but let me put. So yesterday we introduced this CK or C0 space. So we continue. So we have already a notion of bounded. So maybe we go for a bounded one. So let U be a subset in RD. So by subset, unless I tell other way around, this is open subset. Okay. So then we define the set of bounded functions on U. So these are functions from U. So this can be also, yeah, I mean, by subset, I mean, it can also equal to K such that this is bounded. And for such functions or space, we use usually the supremum norm that we introduced yesterday. Let me also introduce again here. So supremum x belongs to U f of x. Remember, yesterday we put this is compact to make sure that this is finite. But since this is finite, we don't need to put compactness here. Okay. Now, one of the prototypical example that we encounter in quantum mechanics is the so-called LP space, or Lebesgue measurable space. So you can define it quite generally. Okay, I am doing it only in RD so that the requirement for measured theoretic and real analysis is bare minimum, but you can do it much more generally. Sorry, there is a question. I did not understand how the equivalence of norm is telling us. Oh, this tells us from the fact that here. So we know from real analysis that if we are only consider C or R as a norm space, then this is a Banach space. Now you see all this norm is defined kind of component wise. So loosely speaking, you know convergence of these things, and then no matter which norm you take, you will take some convergence. And now you can say, okay, it may converge this norm. How do I know it converges this norm? And there comes this equivalence of norm. Is it clear now? Yeah, it's not clear. Feel free to ask again. Let me go to the example. So we have seen actually, yeah, here. So we are going to generalize this notion and this notion. So yeah, to keep the requirement minimum, I am just going to give you or considering subset of RD, but as I told you can do it more generally. So I need some space. So this is functions which are integrable, blah, blah. I'm not writing here. So that the norm is finite. I'm not writing because the right thing is that this has to be measurable function. Okay. And since I don't want to go measure theory at all, although we cannot avoid it completely, but let me bypass for the time being, because it is itself a huge topic. And if you are not familiar, then it will be definitions after definitions. And I don't think I can get something in a very short time. So that's why I'm not writing it, but just tell it. It's a measurable function, which roughly speaking, something that you can measure, or you have a notion of volume. Okay, that's called measurable function. So that this norm, so what you do, you take absolute value of the function, raise it to power p. Before we did sum, but now we are in a continuum. We take integration and we take p to square root. So if this is finite, then this is called LP norm, where p is 1, 2, 3 up to infinity. Now naturally you will ask, how about L infinity? So similar, just we define the now supremum norm. But this is now a bit, so you ask this question, matters. Now you see there is bit matters because we need a bit refined notion of supremum norm. Let me write it, and then so this is something called essential supremum. I shall explain what is this. X and if this is finite. So now question is, what is essential supremum? So essential supremum of f of x is the infimum some number m positive such that you take infimum or vary over all x on u, and then the absolute value of this function is greater than m, has Lebesgue measure zero. Okay, so this is one of the monster I wanted to avoid, but as you see, I cannot avoid. So let me give very heuristic idea if you are not familiar. So by Lebesgue measure zero, you can intuitively think, say you have something here which integrates to zero. Yeah, then you cannot detect whether this thing has been integrated or not. So or say that you integrate two things and one thing just contributes identity in this context, or if you add something, integration of something, so you add integration of something and this thing is zero, then you cannot say whether you added it or not. So these things are called set of measure zero. Yeah, and in fact for measure theory we usually always talk about set of measure zero. So strictly speaking, elements of LP spaces are not function, they are equivalence classes. So why equivalence classes? Because if they differ by measure zero, then we identify. But again, let's not go there. I mean, I would love to go if I have time. Maybe there will be sometimes a course on measure theory or something. But yeah, let me black box for the time being. Okay, so now we have LP space, L infinity space. So we have some functional spaces. All right. So why I have introduced these spaces? One reason is to answer the question some of you asked yesterday. Example. So LP space, these are Hilbert space. And one of this Hilbert space, in particular L2, is of particular interest in quantum mechanics. So now I came back again to your question, does it matter for our understanding? Now you see sometimes it matters. So one of this example, if you look at usual physics book of quantum mechanics, again, please do not get this impression I am preferring one over another. I'm just trying to differentiate what's happening there. You decide what you like or not. So usually it calls that quantum mechanics, you consider operators on a Hilbert space. And the reason is that there is the conservation of probability, which basically means that if you square some function, so p equals to 2, and then you square root, then you get same, or if you don't square 2, then norm is square. Yeah, that's the probability conservation. So since we want probability conservation, which is a very natural thing physically, we need L2 space. So in quantum mechanics, usually we need L2 space, not most general Hilbert space. But In physics literature, usually one does not differentiate between a L2 space and a generic Hilbert space. Now back to your question, does it really hamper? You will see yes, because there are other Hilbert space. Why not L3? It is also Hilbert space, but if you work on L3, most of the physical interpretation will be gone. They will not make sense. Why not some other Hilbert space? These are L. You can define some other Hilbert space. Why not those? Even some Hilbert space has very pathological properties. This will be even horrible for physical understanding. So now you see one instant where this preciseness really matters even for a physical understanding. Yeah. So let me continue the example. Oh, sorry, this is L2. I wanted to write L2. Okay. So LP, okay, and LP new UK for P not equals to 2. These are not inner product space. Okay. We also talked about continuous functions on a compact set yesterday. Let's put R, and where, of course, K is non-empty. This is also not an inner product space. Okay, now we want to give an example which is an inner product space but not complete. And that is the small c, another small c. So this c stands for compact. Maybe I write compact, CPT. Compact. F. So this is an inner product space. But not Hilbert space. In other words, you cannot make this Cauchy completeness in this space. So you ask some example. But by the way, bicompact means that the support of the functions. Maybe I should introduce it somewhere here. Maybe I write it here. Okay, let me write here. So support of a function. Oh no, maybe there. Here. Support of a function is those points of f for which the function is non-zero, and then you take completion. Okay, this is a bit tangential. So then you take this space and with the property each sequence is compactly supported, and that gives you this space. So this is an inner product space but not a Hilbert space. All right, so is it now clear the example you were looking yesterday, or should I talk a bit more? Or yeah, feel free if you have any questions.
Can you explain why these are not inner product space?
I can, but I shall not because that's your homework. So first you suffer and then I shall explain. Sorry. I don't want it to do in a way, but in this way, but we, only 16 lecture. So I have to put something in the thing. So it will be discussed. Let's put it will be discussed in the homework. Okay. So it will be discussed at some point. But yeah, please do not afraid of asking questions so that I will give as a homework. No, I should not. But please go ahead. Any further questions or comments? No? Should we go for a 10-minute break or is okay for everyone or you want a 10-minute break? Yes, maybe 10-minute break is good to or for this abstractness. Yeah, now we are really in the abstract realm of function analysis, and these are really abstract. It's, even for me, I must admit. Okay, since no one wants to have a break, so we can continue. So then let's continue with some properties of Hilbert space. Again, I hope who has done quantum mechanics, you know a lot about Hilbert spaces. There is no way I shall be able to do anything substantial in that set in this time frame. But I plan to discuss a few of these notions that we will use later. So the notion I'm now going to discuss about orthogonality. So definition. Maybe we put an notation for Hilbert space. Where is Hilbert space? Here. So by Hilbert space, we will use this curly H and this inner product. However, usually I will not write this inner product because it's fixed. But when we needed to do it, then we will mention, yeah. Otherwise, I'll not write it. Okay. So we are in a Hilbert space setting. So H. Maybe first time I rewrite here is a Hilbert space. And then we can define something called orthogonal complement. Of a subset, say U of H. So we denote it by, we can give straight U. Oops. U perpendicular is the element of the Hilbert space such that if you take inner product of the vector with any element in U, then this is 0. So those who are familiar with linear algebra, then you have the notion of perpendicular, right? And you see this is nothing but the notion of perpendicularity, but on an infinite dimensional setting. So yesterday there was a question that, do you have a geometry? And I told it depends on the situation. So now I can say, okay, now you see the notion of norm kind of generalize the idea of distance. So geometrically, what you visualize as a distance, norm actually generalize this thing. And inner product space or Hilbert space generalize this notion of angle. Yeah, this is kind of angle because that basically tells you in some ideals, in some small situation, these are perpendicular. So u and v are perpendicular to each other, and that's why this notation. So now you see, in this situation, we have nice geometric intuition or nice geometric interpretation. Yeah. All right. So some of the properties, if U is a closed subspace of H, then we can write the Hilbert space as a direct sum U plus U perpendicular. Although I haven't discussed the direct sum of Hilbert spaces, okay, no, maybe I should discuss because I have used it. So let me discuss it. Now recall so we have, say, two Hilbert spaces, H one, H2, and their direct sum is defined sum direct sum is defined as the set of pairs U1 from U1, H1 and U2 from H2. So H1 cross H2 with, so U1, U2 inner product, and then V1, V2. Oh no, sorry. I don't want to write inner product here. I want to write U1, U2 as a pair like this, and then taking inner product with V1, V2, and this is H1 cross H2. This is given by U1 inner product V1 of H1 plus U2 V2. And then how you go to the sequence? So now we go for the countable sequences. So we use this notation. Direct sum of I equals to 1 to infinity hi. So I think you self-explanatory. You take u1 dot 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 dot. Maybe I have to write at least 2 dot such that ui is this individual hi, the element of Hilbert spaces, and we need completeness or convergence notion. And I haven't discussed it, but if you look at norm space, a norm space is convergent when it is absolutely convergent, which means you basically take sum of absolute value of the elements. And since we are in norm situation, instead of absolute value, we have norm. They converge. Okay, so this is same definition as in the linear algebra, except this is kind of automatic there because it was finite dimension, but not in this case. Okay, so we have orthogonality, and then we also have this nice decomposition. We will use this at some point, but yeah. The next topic, from linear algebra, one way to compute with vector is to use basis, right? We have, for instance, in Rn, we have x e1, e2, or 1, 0, 0, 0, 1, 1, 1, 0, 0, this sort of basis. But now we are in infinite dimensional setting, so we can ask same question, how about the basis? And especially on Rn, one of the nice things is that they are orthonormal, right? So if you multiply 1, 0, 0 with 0, 1, 0, 0, that gives 1, and these are nice relations. So we want also imitate that structure, but in an infinite dimensional setting. And that gives the notion of orthonormal basis. So, okay. H, as before, is a Hilbert space. And this is separable if it admits a countable dense subset. Now, two notions. Countable. So are everyone familiar when we mean by something countable? This same notion from real analysis or even say calculus maybe. So countable means say a set which can be bijectively mapped with set of integers, so that you can count something. Okay, that's countability. Okay, and then there is notion of denseness. So that is very important in the function analysis, especially for differential operator and things we are interested in this course. So by a dense subset, it means that, so say U is a subset of H and is a dense. Okay, this means that if you take closure of U, okay, closure means you take completeness and then you take. So is everyone familiar with the notion of closure? Okay, so who are not familiar, I mean, either raise your voice or write me chat or in a personal chat, because I don't want anyone to left alone. So please raise your voice. Okay, so let me give an intuition, rather a formal definition. Of course, that formal definition is important. So the intuition is that you take, for instance, set of rational numbers Q. Okay. So it's a side remark Q. And then you have set of reals. And then how you get set of rationals to set of reals. So those who know, they know that you basically do completion, and that's one way to construct real numbers, right? And if you're not familiar of this construction, then you intuitively think this way. So real is kind of a continuum thing, right? There are integers, there are rationals, there are irrationals, and all these things. And now when you have a rational and you want to get that, there are some free or gaps, right? So you have to fill those gaps in an appropriate way. Not just filling, but some appropriate way. And there is a well-defined procedure how you complete Q, or even in more general for a metric space, but let's not go there. Yeah, let's come only say R or Q in this context. And then you get reals. And now in this context is same thing. So in R, what you have absolute value, and you use this absolute value to map or to approximate things. On H, you don't have absolute value, but you have a norm. So here you have absolute value function, and here we have norm. So what you do here using absolute value, you do here using norm, and then you do similar thing. Another way to understand this denseness is that, okay, you take any element in H, okay, and then you take a sequence in U. And now, if any element in H can be approximated by some sequence in U, then U is called dense. So if you're not familiar, maybe sequence is useful because we have talked about, say, for instance, Cauchy sequence. So just think this way. This is a big thing, and you take something from here. And this is, okay, maybe I draw. So this is H. And this is U. Now, in general, in this setting, there are elements in H, of course, which are not in U, because H is a bigger space. But it may happen, it may also not, but it may happen that you take any element here, and then there are some sequence by which you can converge to that element. And if it is true for every element of H, then this is called a dense subset. Okay? Maybe I shall discuss it a bit detail later when we talk about operators, because we also need it. But yeah, it might not be known to everyone, so it's better to discuss. But at least, hopefully you get some intuitive notion. Okay, so that's the notion of separability. So the Hilbert space we require mostly for quantum mechanics are separable. Okay, so from now on, by a Hilbert space, we will only mean separable Hilbert space. Although non-separable Hilbert space exists, you can do function analysis there, but for practical purpose, they are not the terribly interesting thing. Okay, now introduce another definition. Let E1 dot E2 dot 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 be a sequence in Hilbert space. So this is called orthonormal if you may guess what. So that's how I'm motivated. Think about this orthonormal basis in Rn. So Ei, Ej equals to delta Ij. Yeah, that's precisely the relation we have in Rn. But that's an infinite dimensional generalization. Okay, now why we talked about this? The reason is a theorem. A separable Hilbert space admits an orthonormal basis. So now you see that separable Hilbert space are kind of closest to the Rn or Cn situation, where you have a nice basis, you can compute thing using writing in terms of basis, and then this gives you another motivation to consider separable Hilbert spaces. So that's another reason, motivation to consider separable Hilbert spaces. All right. Any question? I understand I'm introducing lots of notions without much examples, but yeah, that's kind of. So I wanted to really go fast over Hilbert spaces thing, and not because these are less important, but we really want to prove things on operators, which is the main part. But yeah, maybe I give some time to contemplate, and you can ask if I should explain some of these things more or. Separable Hilbert space, is it uncoupled? Uncoupled with what? Could you explain? I mean, what do you mean by uncoupled or uncoupled? Usually when you say coupled, coupled with something. So by separable Hilbert space means precisely this. So these are Hilbert space which has some subset U which is dense. That means you take an element of Hilbert space and then you take a sequence of elements on H. You can approximate this element using U, and the number of subset will be finite. Sorry, will be countable. You can also think these are the subclass of Hilbert spaces where you have an orthonormal basis. Does it answer your question? Thank you. Any other questions? What is true in infinite dimension? I mean, by is what is it? What does it means? So, do you mean that the separability? Yeah, yeah. This is everything is in infinite dimensional setting. So this H is an infinite dimensional Hilbert space. Yes. Any other questions? Who are already lost? You can write personal message that I am already lost. I don't understand anything. Everything looks completely nonsense. Okay. Any comments? Does this hold on Banach space? You mean the separable notion of separability of in the Banach space setting? Do you mean that? Okay. Uh, I think so, but I cannot really pinpoint. I mean, I cannot see what will go wrong because to define separable, we need notion of denseness. And so once we have a norm, we have topology, so we can define a notion of dense. And countability has nothing independent of Banach space or Hilbert space structure. So I think such notion should exist in the setting of Banach space, but yeah, I cannot just assure you because I don't recall exactly now whether I have seen in a standard reference or not. But I don't see what can go wrong. Let's put it this way. Yeah, maybe some comments is useful because who are mostly from physics background. I also studied physics in my master's. So usually these are not taught in physics literature, as I told. And the reason, as I told, so that there is this demarcation, if you want to say it this way, there is this theoretical physics community and then there is mathematical physics community. And in theoretical physics community, they think this mathematical preciseness, properness, or the way of mathematics, mathematical way of thinking, they think is not necessary. And they're amazing physicists. There is no doubt, and they make a lot of progress. Um, and then that's why in those literature you don't see this sort of presentation or this level of clarity or abstractness the way you want to phrase it. On the other hand, some people or group of people thinks uh, nature can be described in terms of mathematics, and they try to make physical theory mathematically rigor or mathematically well understood, not just in an intuitive level. And then you really need it. For instance, when I first studied Hilbert space, I never understood what's the difference between an Hilbert space and a inner product space. For instance, sometimes people call pre-Hilbert space. So pre-Hilbert space is precisely what is an inner product space. Um, And then from physics books, it's like you don't need it. You just use Hilbert space as a word without really understanding properly what is a Hilbert space. And you can do a lot. There is no doubt. I mean, by a lot, I really mean best top level, top notch research, not only study. But I was not satisfied doing something without at least some level of understanding. So gradually I shifted towards mathematical physics. And the reason to offer this course is for physics background to show the other side of the river, and for math student also the other side of the river where their abstractness has some physical motivation, some physical interpretation, some physical meaning. So you can think is like a bridge where math physics can talk with each other. And historically, as I was telling, if you go back 100 years before, there was another postdoc. Back then it was not a postdoc, it was like a research assistant, also in Göttingen. And he heard about Heisenberg's famous work because Heisenberg was also in Göttingen. And he tried to understand things or mathematically. And he understood that things are not clear or say well-defined objects. And among some other people, he also started to understand quantum mechanics in a precise way. In fact, the word Hilbert space is coined by that postdoc, and he is called John von Neumann. Although it's called Hilbert space, but this is formally defined by von Neumann, and Neumann was a postdoc of Hilbert in Göttingen. So Neumann started the unbounded operator business on Hilbert space just to understand quantum mechanics. What are you explaining was my question since I study. Okay. We want to explain right now what is a Hilbert space and which sort of Hilbert space is necessary for quantum mechanics. That we will discuss later part of this course. We will see, for instance, we have already seen we have this separability notion. So only separable Hilbert space, and later we will see even more concretely, not all separable Hilbert space, but some very specific class of separable Hilbert space is required to formulate quantum mechanics. For instance, if you want to formulate classical canonical anti-commutation relation, you need which Hilbert space you are working. And if you do not know which Hilbert space, then you do not know what is your operators, that we will see shortly. So if you want to really formulate any statement of quantum mechanics in a precise way, in the sense that you really want to understand what these objects are, then you need to know what is a Hilbert space, at least, and then more that we will go. So I try to pick some of the very essential, as you can understand, with 16 lecture, there is no way it's possible, so that you can at least read standard text in quantum mechanics, and now you know what does what mean. So now you know, hopefully, what is a Hilbert space mean. It's not just some word and some notations. Rather, it has a very precise meaning. And time to time, we will also give you some remark where this infinite dimensionality and function analytic aspects has physical consequence. Yeah, we will see some physical consequences. And as I was telling, historically, this subject was developed to understand quantum mechanics and also partial differential equation. But it was mostly quantum mechanics that motivated von Neumann to develop so what we are discussing mostly due to von Neumann, and he developed basically to understand quantum mechanics. So if you want to understand quantum mechanics, you need several things or many things, and some of things we are going to discuss here. For instance, I think after today's lecture, all of you know what is a Hilbert space actually. and what is not a Hilbert space.
Why here every space is a subset of another space? This I don't know. Some sort of confusion.
Please say it again.
Why every space is a subset of some another space? Like the inner product space is a subset of norm space and then matrix space and then as a whole
Okay,
a
because
topological.
oh yeah. So this is this whole umbrella. So perhaps
Yeah.
topological space is the largest, and then norm, and then inner product. So this reason is that you have the unity in mathematics. So although these were developed sometimes not in a systematic way from here to there, but end of the day, we mathematicians have been able to describe a general structure. So everything falls under some very generic structure. And that's why you see this structure. This structure also signifies the development of mathematics in a way is constructive and consistent, right? So things are under some hood. You may have some generalization that doesn't interact with existing things. Sometimes this happened. But I understand you meant this picture. First, you have topological space, and then normed, and then inner product, and then complete inner product, and so on. So this comes because of in mathematics you have a nice structural way of relating things. So we have very generic structure, and then we can reduce assumptions, and you get more concrete structures, and that's why you have this subset picture.
We have already the concept of manifolds in mathematics. So why?
Mm-hmm. So what's the last part of your question after manifold?
Why we don't use the manifolds concept here?
Oh, because vector spaces and manifold has a different. So all vector spaces has manifold structure, but so for finite dimensional, but Hilbert space doesn't has a manifold structure, right? So because Hilbert space are infinite dimension and manifolds are finite dimension, you can define manifold on infinite dimension, and those are defined using Hilbert space. So manifold is not sufficient for the physical object and mathematical object we are treating. For instance, if you consider set of smooth functions on Rn, this is not a manifold. But this is a very important structure, right? If you want to do PDE, you need this structure, but then manifold is not sufficient.
We need some extra structure like symplectic geometry.
Not even symplectic. For instance, if you take this space, let's say in RD. So this is not even a symplectic manifold. This is not even not even a manifold. So how you discuss this structure? This is not a manifold. Definitely, this is not a symplectic manifold. So when you want to analyze things with this structure, then you need topological vector space or Fréchet space. And this is very important, right? Because we talked about solutions of PDE, solutions of Schrödinger equation. So also important in quantum mechanics, because quantum mechanics has some PDE aspect. So then you see that this is one example where manifold is not sufficient. You need something which is, I would not say more manifold, more general, but different structure than a manifold structure. And as I told, sometimes I mean it happens. Hilbert space actually helps to generalize the definition of manifold. So the usual definition of manifold means finite dimensional manifold. If you want to define infinite dimensional manifold, then you precisely use Hilbert space. So infinite dimensional manifold are those whose chart are homeomorphic to Hilbert spaces. So you see that even to generalize the notion of manifold, you need some of this machinery we have developed. Okay, sometimes it would be very effective for us if you can give us an useful phenomena of quantum mechanics after exposing any deep maths definition theorem. Yes, that's why we will do harmonic oscillator as an example. If time permits, I also wanted to do hydrogen atom, but I don't think. But let's at least we will do harmonic oscillator, and things we are developing actually going towards harmonic oscillator. So even going, or even to formulate harmonic oscillator, we need a notion of Hilbert space, we need notion of unbounded operators, and to solve harmonic oscillator, we need spectral theory. And if you look at the content of the course, this is precisely why we put this before going to harmonic oscillator. So yeah, I would request you to be a bit patient, and then we will see very concretely how this notion comes in quantum mechanics. But I take your suggestion. Maybe next time I try to relate some physical picture also with this definition and theorems. But at this point, yeah, I can just give an example. For instance, we give an example for L2 space. So L2 spaces that arises naturally in quantum mechanics, and then you see an example. But yeah, at this point, we don't have actually sufficient tools developed to really talk about some physical situations. So next lecture, we are going to talk about bounded operators and then unbounded operator, and then you start to see. This is somehow unfortunate or requirement. Even to define a quantum harmonic oscillator, you need quite a bit of function analysis. Otherwise, you cannot even define, forget about solving this thing. So be patient, this is coming. So in short, vector space is just an algebra. Inner space is also norm and angles, and Hilbert space, what we have all this property. No, this is not true. All algebra is a vector space, but not a vector space is an algebra, because to define an algebra, you need to have some sort of multiplication, and then the multiplication has to be also element of the set. So far, inner product maps from vector space, or norm maps vector space to the field, not this space. So to define an algebra, you need another, say, maybe you can say cross product, and then you have algebra. So all algebra is a vector space, but not the other way around. And inner space is about norms. Not really. Inner product space is about angles, and norm space is about norms or distances. And Hilbert space is that we have all these properties with limits. Yes, Rastron is true. Hilbert space is a nice space where you have angles, you have distance, and they have a convergence or limit. You're right. Thank you for all these questions. Please go ahead. Any further questions, comments? Even if it's too abstract, feel free. Okay, so if there is no further question, let me start just the very basics that we are going to discuss anyway tomorrow. Operators, kind of the heart of our so since we need some preliminary, let me recall. I think from linear algebra, what is an operator? So an operator, let's consider RD for the time being, is a map from RD to RD, or you can consider, say, a subset of RD, and then you will say, okay, an operator is a map from U to U or RD, right? That's the notion of map or operator in linear algebra you have. So we want to imitate, as before, the same notion, but now in Hilbert space setting. So then intuitively, we want to define a map from a Hilbert space to a Hilbert space. And we will see that this is not always possible. And the reason, or one of the implications, as some of you want to ask about physical, you will see there are interesting physical operators arising in quantum mechanics which doesn't have this property. And this is something called unbounded operators. On the other hand, there are some operators for which this is possible, and these are called bounded operators. So since bounded operators are simpler, we will start with first bounded operators, and then we will go unbounded operator. So let me just start then, maybe slowly. So definition. So by an operator, I write a bit, and operator T on a Hilbert space H, I mean a linear map from domain of T to the Hilbert space, where the domain of T is of course a subset of Hilbert space, but it may, or it is not necessary the whole space. Okay, so you already see one difference. Here we do not have such restriction. We can define in the whole space. Why we cannot do it? You have to patient a bit, but just say as a trailer, in general, this is not always necessarily the whole space. So if you do for whole space, again, this is called bounded operators, and if you can't, these are unbounded operators. Why you can't? We will discuss with detail. Now, as I am telling these words, bounded, unbounded, what does it really mean? So once we have a Hilbert space, then we can define the norm and operator. So before we have a norm of a vector, but now we have a norm and operator. So let me define or denote the set of all operators. By the way, by operator, I will always mean linear operator. Maybe I write here, linear. Okay. And then we use this notion, linear operators on Hilbert space. Although it means this thing, not literally from H to H, but it's just a shortcut notation. Okay. So from this space, we define the norm of an operator on Hilbert space R. And how do we do that? You take an element or an operator, you map it. And the definition is that, okay, you have TU, you have this norm on Hilbert space, you divide out by U, of course, provided this is non-zero, and I think you can get what I'm going to get, supremum over U in domain of T, and make sure there is no zero. So this is an operator norm, and an operator T is called bounded if this is less than or equals to 1. All right. So thank you very much for your kind attention. We are over time. feel free if you have any questions, comments. Otherwise, yeah, we will discuss bounded operator tomorrow. And if you want to see something related, feel free. Then I can also try to prepare. Maybe I stay 10 minutes more if you have questions, comment, or any general query. Difference this math, physics, abstractness, anything, feel free. You can have any positive constant. There is no problem. One is just you can have no problem. So in this case, it is 1 because we have divided out with the vector. Yeah. But if we do not divide out by this vector, then it can be some constant. So basically, this is bounded if this is finite. That's the meaning. Maybe I write this way. Yeah, so you can also write this way. Tu Hilbert space is less than equals to u. So there's the notion of boundlessness, right? So you apply it, you do not go beyond this. That's actually the notion of boundedness. So let's put this way. Okay, so any constant, positive constant, of course. Yeah, in general, it should be infinity. I mean, I shouldn't write 1, but thanks for this question. Any further questions? Okay, if not, then maybe we wrap up today here. Okay, so thank you everyone for your kind attention, and I hope see you all tomorrow.